sorry for the delay. Okay, it's some I don't know why, but some other classes, I mean, tend to remove like the wire in the stand. I mean, so, but anyway, okay. I think we end up. Did we cover this slide and the next one, the Boltzmann distribution? Just want to make sure. So what was the last slide that we covered last time? Do you guys remember?
应该前几页吧。
前几页。这个吗？
再往前进。好，应该是。
Okay.
这一页。
Okay. So. So this okay, so you can see that in this example, okay, we intended intended to make the classes unbalanced, okay, in the sense that where is it? Yeah, from here you can see that we only get like a 5, no, because we get rid of the first 45 entries from the Setosa class, okay, and but we keep the last one, okay, the Viscala, like all the entries in the vessel class. So the ratio for these two classes is 5 to 50, okay, 1 to 10, okay. So intentionally, pick this one, okay, like that, and then we pretty much feed that into the same model, okay. So the result figure, okay, is like this, and you can see the boundary, okay, is more leaning toward the minority class, okay, the minority class, which is indicated by the blue dots, okay. The blue dots are the Setosa, and the other one is the Viscala, okay. So this is an example that show you what the unbalanced data is going to do to the data analysis, okay. So what do we do, okay, if we find unbalanced data? I mean, the easiest solution is that if you are able to control the data collection, okay, if you are assuming you are able to control data collection, then you probably want to get the data set with roughly the same number for each class, okay. I mean, so how do we consider, I mean, the classes, I mean, have roughly the same number? It doesn't have to be exactly 1-to-1 ratio, to be honest, okay. I mean, if you are into machine learning, okay, you will observe that, okay, of course, like the example that we observed, like, previously, like if the ratio is 1 to 10, okay, then obviously we have this unbalanced data problem, okay. But if the data set, for example, if you have two classes and the ratio is maybe 1 to 2, even 1 to 3, okay, I mean, if you just look at the number, yeah, I mean, they are not equal, of course. I mean, because yeah, I mean, the minority class is still like a couple of times lower than the majority one. But if it's like 1 to 2 or 1 to 3, normally your analysis result will still be valid. Okay, so this unbalanced data classes problem, okay, is not necessarily like happen that strictly, okay. It only happens when the minority class is like at least like one order lower than in terms of ratio, one order lower than the majority class. Okay, maybe 1 to 10 or even lower than that, then you normally have that issue. But if it's like 1 to 2, 1 to 3, okay, normally you do not need to worry about this impact too much. Okay, so of course this is the case. I mean, when you also deal with data collection. Okay, if you collect the data and you have control over like how many entries, how many examples you want to collect for each class, then this obviously is a good solution, right? Yeah, but unfortunately, okay, if you have no control over the data collection, okay, then you need to be careful when you interpret the result of this analysis, okay? So you have to check the uncertainty of the model and run some posterior predictive check, okay? So we have done that, I mean, many times, okay? But this becomes especially important when the data set is unbalanced, because yeah, I mean, the result may not be correct, because as I said, like the boundary will leaning toward the minority class. I mean, when this boundary is leaning too much toward the minority class, and it's not going to, I mean, give you a very good analysis result. So so another option will be to input more prior information, okay, because obviously like for this minority class, okay, I mean, you can try to provide certain prior information to fix this bias, but this is it depends on how much you know about this data set, okay? Every time when we talk about like to provide like a stronger prior, it always involve like what kind of data. I mean, how much you know about this data, okay? You cannot just provide an arbitrary strong prior and assume that will be okay. Okay, so this is like you can, another way is you can run alternative model. Okay, I mean, I'm not sure if we are able to talk about that. I mean, because this is the model comparison chapter. Okay, today I'm trying to at least finish this chapter, and we still have like 1 week of class. So I'm going to, if I'm able to talk a little bit about the model comparison today, if I'm lucky, I probably can finish like less than half of that chapter. Yeah, that's the best I could do. Okay, but anyway, let's see what happens. Okay, and then the next topic is the softmax regression. Okay, what is softmax regression? The softmax regression, the function looks like this. Okay, softmax I mu, okay, where mu is actually a vector. Okay, a vector with like maybe n components. Okay, n components. So you have mu1, mu2, mu3, okay, up to mu n. Okay, and so for each component, for each output component, okay, softmax I mu is going to be, you can see it's a summation of exponential of mu k. Okay, I mean, and the nominator is the exponential mu I. Okay, so first, okay, from this equation, you can tell that, okay, because that's like all the terms will be put into the power, right? So it's e to a power, where that power is a term of your input, right? Is so in that case, okay, you can imagine all this exp mu I, okay, no matter which mu I you are talking about, I mean mu 1, mu 2, mu 3, up to mu n, okay, which mu I you are talking about, okay, exp to the power of mu I, it's going to be positive, right? Positive, I mean it cannot be negative, right? Okay, it can never be negative. And the second, okay, you can imagine, okay, for each term, for each softmax I, okay, obviously, okay, this result, okay, this result is going to be in the range of 0 and 1, right? Because the denominator is the sum of all the term, okay? So it's going to be exp mu 1 plus exp mu 2 plus exp mu 3 plus blah, 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 plus exp mu n. And then your numerator is one of those, right? So, it's going to be, the result is going to be in between 0 and 1, right? So this is the second thing. The third thing is what? The third thing you can observe is that, okay, the sum of all the terms, from this softmax, wow, how come this is so the sum of softmax I mu, okay, I from 1 to n, okay, this is going to be 1, right? Right? Because the denominator are all the same, right? And numerator, when you add up all the numerator, it's going to be exactly the same as denominator, right? Right? So what does that remind you? What does that remind you? I mean, first, each item, each I, okay, each component of the softmax result, the range is between 0 and 1. Second, if you add up all these terms, okay, the result is going to be just 1. And each of them obviously is, is positive, right? So doesn't that look just like a probability for you? It looks just like a probability, okay? And it is, okay? This softmax regression, okay, is used for, to classify n classes, okay? It's used to classify n classes. In the previous example, okay, the logistic regression, okay, we talk about binary classification, right? But now, okay, for this, okay, the softmax regression, we are actually talking about, we are going to use that for the multi-class classification. Okay, multi-class classification. Okay, so, okay, softmax guarantee, we get positive value. That sum up to 1. Okay, that's obviously the case. Okay, so the softmax function is reduced to logistic function when k is 2. When your n is 2, okay, the k here is the n I'm referring here. But when the total terms is 2, or the number of classes is 2, okay, obviously, okay, the softmax function should be reduced to logistic one, right? Because logistic function is used for binary classification, which means there are two classes, right? And the logistic function is going to output the probability of the positive class, right? And the other part obviously is 1 minus probability of positive class is probability of negative class. I mean, so which means like the logistic function also output the probability for two classes, pretty much, right? So conceptually they are exactly the same. I mean, you can check, you can verify this by yourself, okay? But I just want you to understand that softmax is softmax is an extension of logistic function, okay? I mean, in the sense that, I mean, one is used for multi-class classification, one is used for binary classification. So, and as a side note, the softmax function has the same form as the Boltzmann distribution used in statistics mechanics, okay? So this Boltzmann distribution is normally used for, like, in the physics, okay, which is used to deal with probabilistic description of atomic and the molecular system, like this type of system. I mean, when they describe it, okay, they use Boltzmann distribution, but I mean, and there's like a parameter called temperature T, okay, that divides mu. Okay, when T goes to infinity, the probability distribution becomes flat. So all states are equally likely, and when T equal to 0, okay, approach 0, the most probable state, okay, will be 1, and the other, like states will become close to 0. Okay, it will become, softmax will behave just like a max function. I mean, so this actually you just need to think about this a little bit, because really like in Bayesian data analysis, this is not that important. If you are into physics, obviously this is important for you. If you are because the author, okay, remember I told you, author is the guy who is into quantum chemistry, right? So he obviously has a very strong background in physics and chemistry, okay? So that's why he was talking about this. But this is not that useful for if you are not into that field, okay? So not only we need to replace the logistic with the softmax, okay, if you want to do like a multi-class classification, you also need to replace the Bernoulli distribution with the categorical distribution, okay? So the categorical distribution is the generalization of Bernoulli, okay, to more than two outcomes, okay? And the Bernoulli distribution, okay, which represents a single flip, is a special case of binomial, okay, which represents n coin flips. So the categorical, okay, which represents a single row of die, okay. I mean, this is just an example because die has like the outcome of die has has 6 outcomes, right, from 1 to 6, okay. So it just represents like one multi-class classification result, okay. So categorical is a special case of multinomial distribution. This multinomial distribution represents like n rows of a die, okay. But right now, of course, I mean, we only need to use the categorical. That's good enough, okay. So so what example do we use? I mean, for this multi-class classification, obviously we can still use that iris data set, okay, because iris data set in the previous examples, we only use 2 out of those 3 classes, right? Okay, but now, okay, with the ability to deal with multi-class classification, we could like consider the whole data set, okay, now, okay. So you can see that we use all the 3 classes, Setosa, Vesicaler, and Virginica, okay. And also, I mean, we try to make use of all the features. There are 4 features, okay, sepal length, sepal width, payload length, payload width. I mean, we talked about this, I mean, previously already, right? So we are also going to standardize the data. I mean, so that's represented in the last line, okay? So each data, okay, we subtract the mean of that, and also we divide the standard deviation. So we normalize like each feature, okay? But okay, we could have also just centered the data. We don't have to normalize the data. I mean, for like a better result, okay, we need to at least center the data, okay? So this also gives you an idea, like remember like when you need to deal with that the term project, you could try like standardize the data, or you can consider, I mean, at least center the data, okay? So anyway, okay, so once we have done that, okay, we will create a model for that multi-class classification, and you can see that this is actually a very simple one, okay? So the alpha, beta, okay, they pretty much like similar to what we have done previously, okay? And the mu, okay, is the alpha plus like, your max multiplication result, xs and beta, okay? Remember, this xs and the beta are both like in matrix form, okay, in the matrix form. So you can see it's a 4-3, shape is 4-3, okay? It's 4-3 because we have 3 classes and we have 4 features, okay, by the way. And then, okay, we have this theta equal to tt dot nnet dot softmax. This tt just like it's an abbreviation of Steno, okay, Steno dot tensor prefix, okay, Steno dot tensor prefix. So we just abbreviate it as tt, okay. And I mean, this statement actually calls the softmax function, which is provided, I mean, under the Steno.tensor package, okay? So we apply the softmax, okay, on this mu. Remember, this mu is a vector with 3 components, okay, because this is 3 classes. So once you apply that, we get like a probability for those 3 classes, and then we feed that into categorical, okay, and we put p equal to theta, observed equal to ys, and and we try to generate like samples, 2,000 samples, okay. So that's it, okay. So if you try it out and run the code, okay. You will find that, okay, yeah, this is like you can try to see like the result of this model on the data set, and this is a piece of code, and then the result is that the data set is, this model is able to classify 98% of the data set correctly, okay. Obviously, this is very good, okay. Only 3 entries are misclassified, okay. So but is it that good? Is there like any problem with that? Obviously, okay. Here, okay, what we try to do is that we actually try to use the training data set to verify the effectiveness, the correctness of the model. But keep in mind, the model is trained by the training data set. So obviously, if you use the training data set to verify the model performance, obviously it's going to give you a much better one, okay? So normally, okay, what happens is that what we want is like you want to reserve like a portion of the data okay, for the as a test data set, okay, and use that to evaluate the model performance. Okay, you don't want to, use the training data set to verify the model performance because obviously there's a bias. Okay, the model is already trained on this data set. So it obviously should perform much better. Okay, on this data set. So this is like actually it gives us the overestimate. We overestimate the ability of the model. Okay, so we don't want to do that. So that's why I say like we want to divide the data set into training data set. Sometimes we even want to divide it into training, validation, and the test data set. So so the takeaway here is don't use the training data set to evaluate the model performance. Okay, otherwise you are going to overestimate the performance of your model. Okay, so anyway, one more thing to talk about is that you can run the posterior predictive check and you can run the summary of this result, and you will find that the marginal distribution of each parameter, are very wide. The posterior are very wide. Okay, the 96%, right? Posterior, the PD, is going to be very wide. Okay, for different parameters. Okay, so they are as wide as indicated by the priors. Okay, so how come it doesn't shrink the distribution after we incorporate the data? Okay, so there's some problem, right? But make no mistake. Okay, the model performance, even though we overestimate it, by using the same training data for estimation, but the model performs okay. But the problem is like the posterior of your parameters, doesn't look right? So even when we were able to make correct predictions out of the model, so this does not look okay. What happens? So this is the same non-identifiability problem that we already encountered for correlated data, in the regression model. Remember, if you have two variables that are very, very highly correlated, you will find that it is difficult to control the posterior of those like highly correlated parameters, right? That's pretty much the same issue here. In this case, the y posterior is due to the condition that all probabilities must sum to 1. This is obviously the case. But this one, look at this model. Even though this model, is a correct one, it's a perfect, fine model, but the issue is that this model does not include that restriction here, right? Because all the probability has to, sum up to 1. Obviously, this is one more restriction, right? It's one more restriction that is not considered in the model construction. So what do we do? Given this condition, we are using more parameters, then we need to fully specify the model. So it's kind of like you have more condition than the number of parameters, number of variables in the model. So in simple terms, if you have 10 numbers that sum to 1, if you have 10 numbers, if we know like there are 10 numbers, they will be summed to 1. You just need to give me 9 of them, right? Because the other one we can calculate to get it, right? Okay, same here. Okay, same here. One solution is to fix the extra parameters to some value. So we intentionally fix an extra parameters, one extra parameter to some value. Okay, for example, to fix that to 0, and so that this problem can go away. So this is the improved multi-class classification model. Okay, over the previous one, obviously. Okay, so the first two terms, the only one you can see, the second one you can see that the shape is no longer 4-3, it's 4-2. So in the sense that we only output the probability of 2 classes, because the third one we can compute. That's exactly what we are talking about here. And then, okay, so the third one, okay, see, we intentionally concate a 0 to alpha, and the concate like we use NumPy zeros to generate like some number of zeros, and concate that to the matrix. Okay, and then the other part will be exactly the same. Okay, so we intentionally put like a one class, okay, to be 0. And the result is actually better than the previous one. Okay, it should give us the same model in the sense of the performance. The model performs the same, exactly as good. But now, if you look at like the distribution of the posterior for like different parameters, they will look much better. Okay, so so far, okay, we have discussed the logistic regression and a few extensions, okay, such as like softmax, okay, regression, okay. Oh, by the way, the previous example, this is called softmax regression, okay. If you use softmax as like to replace logistic, that's normally how we call it, okay. So in all cases, we try to direct compute the P of Y given the condition of X, okay. So that's the probability of a given class not knowing X, okay, with X being the features, or you can say the X being the data, okay. So we measured 2 members of the classes, okay. So in other words, we try to directly model the mapping from the independent variables to the dependent variables, okay. So we try to find this mapping directly, and then use a threshold to turn the continuous. Remember, the result we are getting, okay, it's going to be a probability distribution, right? Okay, you are going to get a probability for different classes, okay, and the probability obviously is a continuous result, right? We are going to turn, and then we use like the boundary to cut like the continuous result into discrete boundaries, okay? So the boundary is used to divide the continuous result into discrete classes, right? That's how we did it, okay? That's how we did it. That is what, well, even this one, see, this is like this boundary that we generated is used to divide a continuous result into like a discrete one. And the one that is even more obvious is this this one. Yeah, this is the boundary, right? Obviously the result is a continuous result, but we we use a boundary to determine to break it into two classes, right? So this is always the case, okay, for the logistic regression or softmax regression, okay. But, okay, so this approach is not unique. There are other approaches out there. Okay, what is the other approach? Okay, one alternative is to first model P of X on condition of Y. Okay, this is the distribution of X for each class. Okay, and then assign the classes. Okay, so this one, okay, we try to get Py on condition of X. But this one, okay, we first model P of X on condition of Y. Okay, so that's exactly the opposite. Okay, so this kind of model is called a generative classifier. Okay, I mean, I know recently the generative model is popular in AI. Okay, for example, the ChatGPT is one of the most well-known generative models. Okay, but this in the Bayesian data analysis, we also have this type of generative classifier. Okay, this generative classifier, we are able to create. We can generate samples from each classes. Okay, so the previous approach, the regression model, okay, regression-based model, is not able to generate sample for each class. Okay, but this generative classifier is able to do that. So this is one big advantage over the regression models. Okay, such as logistic regression or softmax regression. Okay, so on the other hand, logistic regression is a type of discriminative classifier. Okay, so it's a discriminative classifier because it tries to classify by discriminating classes. Okay, so we are trying to create classes from the continuous space. So that in mathematical term, we call that we are discriminative classifier. We call that discriminative classifier. So, but we cannot generate examples from each class from the model. Okay, so this is the drawback of that. But obviously, it can be used to classify for the classified purpose. Very well. Okay, so we are not going to go into much detail here about generative models. Okay, for classification, but we are going to see one example that illustrates the core of this type of model for classification. So we are going to show you one example of this generative classifier. Okay, so we are going to do it for two classes and only one feature to make our case simple. Okay, we restrict the problem into just two classes and one feature here. Okay, so just like the first model we built, in this chapter. Okay, remember the first model the first logistic regression model we built for this chapter is we consider two classes and one feature. Okay, that's the S shape and the boundary that we are getting. Okay, that one. Okay, so we are going to use exactly the same class, same data set. Okay, two classes, one feature. Okay, so we so far as PyMC3 implementation of generative classifier. Okay, yeah. Let's take 10 minutes break. When we come back, let's talk about this this model. Okay, let's take 10 minutes break first. Okay, is it good? Okay,